Um, the next session will be like the first session of a couple of sessions about about the zero knowledge proofs. So we conducted a polls about for mathematics background level, and the other is like ZK. We got the votes, and but today's session is about like a ZKP FAQ. I would like to answer any question from you that about anything that don't understand or kind of want to know about, or where the terms come from, or what that mean. Okay. And the next session from tomorrow and up to the Friday, I will start from a very basic minimal protocols, all the way to next week about how to build a modern Zk-SNARK proving system like a Planck. Yeah, feel free to interrupt me for asking any questions. So, okay, I will use whiteboard. So, I think there will be more mentors coming, and they will share something more mathematics. But my talk kind of more intuitive. So, share you something like the basic intuition, like how the zero proof works, and yeah, some basic idea of that. Okay, the first topic will be, we start. ZKP, okay. Can you see my drawing? Is that small? Okay. Okay, zero knowledge proof. So how many of you understand what does the zero knowledge mean? Okay, please raise your hand if you can explain that, what the exact definition of zero knowledge. If you know the definition, then you raise your hand. So just a quick question. Okay, 1, 2, 3, 4, 5, 6. Okay, gentlemen, you're the first, raise your hand, the first person go. Can you give us a definition and what the zero knowledge means?
Yeah, well. Yeah, well, the definition that I know is like you can prove something that is true or false without telling details about it.
Okay. Okay, thank you very much. Okay. Okay, I mean, literally, zero knowledge means zero knowledge, all right? That means that, for example, in any communication, that no knowledge can be leaked, right, to the third parties, right? But actually, the zero knowledge has a rigorous formal mathematical definition. Yeah, I will show you later on, and step by step to show why we call it a zero knowledge. What does zero means, and what does knowledge means? Okay. First of all, let's go from okay, what is zero knowledge proof? Zero knowledge proof is the term from computer science, from early days, like the way scientists they did research on how to mathematically define the computation and the computation complexity, something like that, computational theory or commutability theory. Then they extend the definition of what proof is. So in the, from ancient Greek, the Greeks, and the proof is like a mathematical proof, right? So when we're in a high school or middle school, we have to write, some mathematical proofs. For example, for some I don't know how to say in English, some math proofs. Like write down from a proof, something like we write a proof, and then we write something in between, right? And then in the end we will write something like QED, right? To say, okay, here that everything is clear, that every reasoning is like correct or intuitive, and then convince us that every step is correct. Then finally we got the QED, and then the conclusion of just right before the QED is like exactly a statement stated in the theorem, right? So it's like a mathematical proof. So during the 1980s, this computer science, they extend the concept of mathematical proof from the one-way proof to the much broader concept called the interactive proof. So, okay, here we have two roles in this game, in a mathematical proof game. One is a prover, and the other is a verifier. So the prover, the task of prover is writing all the script, right? The script of the proof. And the verifier will check carefully about every step of the reasoning, right? So it's kind of a one-way proof, right? The prover wrote the whole transcript and pack it into a data file or something, or write it on paper and send the paper to the verifier, and the verifier then the following job and verify each step. It's a one-way, or we call it non-interactive proof. But here, if we allow the prover and the verifier, they can communicate, in multiple rounds. Then it turns out the prover can prove something more easier, or prove more, more stuff. Okay. Just imagine that. Okay. When we did something like an examination, final examination, the teacher gave us a paper. There was some statement or theorem I have to prove. Okay, this is one-way proof. But imagine that if the teacher can, it's an interactive proof that, okay, we just write down nothing and submit the paper to the teacher, and then teacher will ask us, okay, I want you to prove something, but you hand out nothing. So, but I will ask you many questions, and if you successfully answer the correct answer, an answer that I will be convinced that, okay, you know the answer, or you know the proof, but you just didn't write it on paper. So I will give you 100 score, kind of. It's like a multiple round proof. So for each step, the verifier will ask questions to challenge if the prover knows something about either a mathematical proof or something that beyond math, beyond mathematics. Okay. This kind of multiple rounds interactive proof, so we call it IP, interactive proof. It turns out in terms of computer science, the problem can be proved by the one-way mathematical proof is actually the subset of the problem can be proved using interaction. So we got the here. Something we could use the mathematical proof. A subset of IP proof. The magic behind this simple idea is like the verifier can challenge the prover And the prover even can use a way to convince verifier without leak anything about the proof, either the proof or something inside the proof or inside. So this is called zero-knowledge proof. Okay, it's doable. And maybe you think if when you first time met this kind of concept, you may thinking kind of okay, it's unbelievable, right? But we can show you many small examples that yeah, it is achievable, it's doable. Okay, I think. Yeah, let's now go to some basic ideas behind this new game, that's a multiple round interactive proof. And sometimes maybe the prover, they don't want leak any privacy or something secret. For example, prover claim that prover got some proof of very famous open theorem, and then convince the verifier or convince the other people in the world that okay, I got something, but I don't want to tell you guys any details. Now I can use the general proof to prove this theorem. Okay. So in the multiple rounds interactive proof, the prover and the verifier, they should have something in common, some knowledge in common, like what exactly the statement the prover wants to prove. Okay, we got a statement. The statement should be clear. Statement is a theorem, should be clear to the verifier. And then the prover will, okay, in the statement, there's something called the like parameters, like I use the x, the vector of x, in multiple values. And the prover also has some we call the witness. This word witness kind of you can say these words occurred in many articles describing the ZKP articles. They are not proofs, but witness has some meaning in the name came from the computer science about the computational complexity theory. So the prover will have x as public input. Okay, x means public input, and a witness. Witness means secret. Some prover don't want known. The witness is known by others, including a verifier. And then there may be something like a common parameters. Okay, for different approaches or different protocols, the parameter is called the public parameter, PP. Public parameters can be very, very different. So basically, the prover prove the statement's whole. For example, that use one letter to denote the statement. Okay, it's a R, a capital R means relation. So okay. Like R, X, so PP here, X, W as witness as secret holds. But here, the witness can be invisible to verifier. So, but we should have something like a X, like a public input. So, public input is kind of a parameter to of some statement. For example, one wants to prove that. I'll give you a small example. H, the little h equals to hash, something like a W. So the prover can prove that, okay, there exists some W when we do SHA-256. I've got a hash, little h, send h to verifier. Then Basically, the prover proved that okay, there is a preimage of H, so H is not something random. It's actually the image of hash of something that the verifier doesn't know. Okay, in this example, okay, what is the statement? A statement is like R. Okay, let me. So what is the public input? Okay, in this example, public input is kind of empty, but probably we can put something a string, a public string here to hash them together. This concatenation. Okay. Here the public input, public is the string. And what is witness? The witness is the W, something that the verifier doesn't know. And also public input, okay, here is H is also public input. So the statement that prover wants to prove, okay, to the verifier is like, there exists some, okay, that's more like more math. Statement that verifier wants to prove is there exists W such that H equals to hash equals to H. So it's a statement. Okay. Okay, so far, any question about this tiny example to show that, okay, basically we can use some proving system. We do multiple rounds, but I haven't shown you any details about how can we do that. But it's an interface of this protocol. And the prover wants to prove something to the verifier. This is a statement. There's a public input and a witness. Okay, basically, if we can use any modern dictionary system or even some minimal, simpler proof protocol, then we can also do this. Okay, so far, any question? No? Okay, good.
Witness is private database.
Sorry?
Witness is private database.
Sorry, witness?
And witness is a private input.
Yeah, private input. Yeah, you can call it a private input. Okay, yeah. Okay, any question? Any question? Okay. Okay, no question. Okay, let's go. Okay, the next term that I want to explain is like a circuit. Circuit. Sorry. Okay, sir. A question? Okay.
So we were talking that the kind of groups that will be interactive.
So yeah.
So we are talking about having multiple rounds.
Yeah.
The challenge.
Yeah.
How it's going to look there? There's only a witness that will produce the hash and the public input.
Yeah, no.
So we only need one round in that sample.
Oh yeah, okay. Basically, you want if the prover can successfully convince the verifier, there will be multiple rounds. But currently we just explain the interface of this protocol without any details about the inside. Yeah, so, yeah. Okay, the second term will be like more confusing. It's about circuit. So circuit is very important, right? I think some of you have the experiences about writing a circuit, either using some modern circuit language like NOR or something like a Circum, or just using the native Rust to write something, for example, for the Hello 2 or Funk, or Cairo language to write some circuit. So, so why should we use circuit instead of anything else? But currently we have another option, like we can use ZKP. But the idea is similar. That how should we use circuit? Circuit is like, so for general proofs, the computer science, prove this theorem that basically we can, the prover can verify a set of problems. The set of problems called NP. NP is like, as P is not, whether it's not equal to NP, okay, that NP. NP is a term from computer science. So this way, okay, if there's any problem inside this set, this circle, okay, basically the prover can use their own proof to prove it in a sometimes efficient way. So, but okay, what are problems that belong into this set? Okay, for example, there are many problems falling into this NP set. Okay, the first problem is like the satisfiability of arithmetic circuit or Boolean circuit. So I should write here circuit satisfiability. It's kind of okay, if we want to prove something, if the problem can be modeled by arithmetic circuit, then we can reduce the proving to something that can be proved by general proofs. So the circuit satisfiability just falls into this NP set. It means that, okay, also at the same time, in the arithmetic circuit, we have only two gates, two types of gates. First is addition, and the other is multiplication. So in computer science, or no, sorry, in the mathematical foundation, like a theory, basically we can model any terminated computation by using addition and multiplication. So in theory, we can for general computation, I mean the terminated general computation, we just exclude the computation with infinite loop something. We can model the computation into circuit, and because the circuit stability can be, falls into the problem falls into NP set, then we can use their own proofs. Okay, then we have a very important conclusion that the general computation, which is terminated, then can be proved in zero knowledge. Okay. Maybe you are confused about what exactly is circuit satisfiability. I will give you explanation. What is circuit? Circuit is like, looks simple. We have many gates, and between gates we have wires. we have, remember that we have two types of gate, addition or multiplication. So addition or multiplication. So what exactly the problem of circuit satisfiability? It means that, okay. For example, here is the public input, is the input A. Then here is the output. Okay, in this tiny example, the output is the little h, right? Here the A is actually, let me use the whole lot. And then here is probably the W, right? It's a private input. Okay, it's a private input. And here's another private input, for example, something C or something like this. So the circuit, so if you have more assigned values to every input of the circuit, then basically we can get the output, right? We just do basic arithmetics. Okay, W, probably, just quickly. Okay, I can just use this circuit to represent the hash function, but in reality, the hash function will have thousands of gates. But here, just for simplicity. Okay. Then if we, me as a prover, I put the inputs, both public inputs and private inputs or witness into the circuit. Then basically we can calculate the output, right, as little h there. But for the verifier, because the verifier doesn't know here, the verifier, without knowing W and C, so how can the verifier ensure that this circuit is satisfiable or not? So there's some situation that some circuit cannot be satisfied. That means, okay, whatever W is or whatever value C is, this circuit, the output of this circuit will not equal to a little h. Okay. So if the prover can successfully prove the statement, that it means the circuit actually is satisfiable. But for verifier only knows the output and the public input. So if verifier by himself, basically he cannot, or very hard to compute, to calculate another W and C to make sure the circuit is satisfiable. So from output and a whole lot to compute W and C is very difficult. It's called an NPC problem. NPC problem is like the most difficult question or problem inside NP. So circuit satisfiability is an NPC problem. So for the verifier will very hard for a verifier to compute C and W. And the prover has the solution W and C, and the prover will show the fact, okay, this circuit is satisfiable by some existence of C and W, but the prover don't want to tell what the exact value of C and W. Okay, here I will introduce you another very important term called knowledge. So zero knowledge. Okay, what does knowledge mean? Okay, C and W and all the values in between these gates are called knowledge. Okay, knowledge is different from the concept of information. So basically anything I draw on the whiteboard are information, right? Something may be pretty random noise. But here in this circuit, so imagine that circuit is huge, probably 1 million gates. But the verifier only has the public part, public input or public output. All the private input, the verifier has using intensive computational resources to calculate all the values of WC and all the values in between. So it is very difficult. So zero knowledge proof means, in this case, in this example, is like the prover has knowledge of W and C, and just to show a fact to the verifier, okay, this circuit is satisfiable without telling you what exact value of C and W. Okay, this is exactly the meaning of zero knowledge proof. So basically, zero knowledge proof can do things more than NP and NPC. Okay, so in the conjuncture, that what is the IP does in a much bigger, it's just a conjuncture. It's not, has not been proved. But most computer scientists, they guess the IP set is much larger than the NP set. But NP set for us is enough. I think for most applications, they are enough, because general computation, if the computation is terminated, then we can model the computation into an arithmetic circuit, and the arithmetic circuit satisfiability falls into only the NP, right? NP problem. Okay, here's some intuition behind the zero knowledge proof. So I hope you can put this drawing on your mind to identify, okay, what does knowledge mean and does a proof mean. But till now, I haven't said anything about the details inside the protocol. So in the following session, I will show you some minimal protocols to understand, okay, how this part works. Okay. Today, I just explain some terms that maybe you heard a lot of time, but where it come from, what they are actually meaning. So I just today explain this concept to you. Okay, so far, any question? Okay, good.
Would you say that the circuit?
Will you say the circuit is a way to factor the final polynomial?
Sorry?
Will you say the circuit is a way to factor the final polynomial that we will use in the...
Factorize the polynomial?
Yes. For example, like you have all as a public input, the W, and then you are like sum or multiply to get the final.
Okay. Generally, we will use polynomials I will explain later on. So we generally use polynomials. Polynomials are very important mathematical tools. So we can describe the relationship between gates. So I will explain that later on. So any questions so far other than polynomial? Any? Okay, good. Is this one?
Can you give a quick recap about the parameters and inputs of ZKP and...
Okay.
Like a quick recap.
Okay. Okay, in the typical ZKP process, that first we have something public parameters. For example, in Group 16, the public parameters can be something we got after the trusted setup ceremony. For like zero knowledge proof in the cache or something, the public parameter can be random chosen little curve point. Because the period verifier, they will use some math under the hood, right? So they have to agree on some common parameters. They're very important, either for cryptographic assumptions or for some pre-processing phase. Okay, actually, the public parameters can be, right now it's pretty abstract, but for different flavors of these arcs or the proofs, it can be anything. Yeah. But X is an input. For example, if we write a circuit, the circuit can be actually prove a family of problem, right? So because we can choose what the public input hola and what it is, and the output of the hash circuit. So X is like, okay, that's like an instance, right? Circuit is kind of, okay, it's like a hash, a commutation, and the public input can be the output of the hash or partial input of the hash. And the witness, like the private input plus all the values in between. That part can should be kept private. Otherwise, the verifier, imagine that, okay, some value in the between, somehow the verifier got that value. That value, okay, we call it the knowledge, right? The verifier will got that knowledge. Then verifier will have, probably half of computation resources can calculate the result of C and W. So it means that the verifier got some slightly more knowledge to equal to the verifier got more computational resources. So knowledge equal to computational resources as the measurement. So does it answer your question? Okay. Any other question? So feel free to interrupt me. Okay, we still have 20 minutes. Okay, no more questions. Okay.
Could you explain a little bit more about the constraints?
Yeah.
And the equations related to the gates,
Mm-hmm.
the circuit.
Yeah.
So what's C in that context?
Okay, say maybe okay, so far C can be a private input also, yeah. Yeah, any private input, yeah, yes. Okay, if no.
It's another witness.
Yeah, witness, yes. Yeah, I think, let me. Yes, you're right. Yeah, here's C should be witness. Probably, I should, right? W prime, something like that. Okay, next topic will be like, okay, let's jump into the ZKP part. Okay, the third topic is ZK-SNARK. Okay, a pretty popular word. Okay, let's just explain word by word. Okay, letter by letter, what does that mean? Okay, ZK means zero knowledge. Okay, first of all, ZK-SNARK is a subset of ZKP. It's a kind of a zero knowledge proof, but it has some features. So ZK is called Z zero knowledge, and S succinctness. S succinctness. It means that the proof size is smaller than the problem, the size of the problem. For example, the size of proof is smaller than the size of a circuit. The succinctness of S, why ZK-SNARK is so useful in crypto or in blockchain, because basically we can compress a huge computation, right? It's for example, 1 million or 1 billion size of circuit, that we can create a much more smaller proof, much smaller than circuit. That means that the verifier, because the smaller the proof, the less computation consumed by the verifier. So it introduces an unbalance between prover and the verifier. It means that the prover will pay more computation to compress something, and but the verifier will be happier because the verifier can use just very small computing sources to verify the proof, whether it's valid or not. But not all of the zero knowledge proof satisfy this, has this feature. But in ZK-SNARK, we emphasize, okay, S is very, very important, especially in the blockchain. Okay, what is N? The N means the non-interactive. So N means non-interactive because, as I mentioned before, so computer scientists extend the concept from one way or one round mathematical proof to the multiple round proof. But here we have some limitation in applications because it has to, the verifier has to be online, right? The prover and the verifier, they should interact with each other. So by in application of blockchain, the prover just does something offline and then submit proof and disappear. So it means that, okay, we should, actually the non-interaction is very important. Non-interaction means one round interaction. That means that the prover just do something offline or off-chain and using a lot of computer sources and generate a proof. And then send the proof to the verifier, probably by email or a message, something, or send it to the third party, and then third party submit the proof to any verifier. So N means non-interactive, right? Non-interactive is so important. But there are some proofs, which don't fall into a non-interaction. It's called interactive proof. For example, let's say the ZK-TLS something. There are some protocols from multiple party computation, and then they will introduce more communication, and the proof size is much bigger. But the proving time can be small. It can be very efficient for a prover. So, but in my session, we just focus on SNARK. Okay, N means non-interactive, and AR means the argument. So argument is another name of proof. But why we bother with another name, right? Another name, argument, instead of just using proof, right? Why do we just put proof here? We use another weird word, argument. So anyone knows the reason or anyone knows the definition argument? Can you raise your hand? Why? Okay. Can you explain?
No, it's just like,
Yeah.
Is it what is being sent? Something is calling the ZKP star? Like you're sending the proof of an argument.
Can you repeat again?
Like, is it something that is being sent to when you are verifying that proof?
Mm-hmm.
Like that argument is whatever the person calling it is sending over? Maybe, I don't know.
No. I'm sorry.
Good try.
Okay. Sorry?
There are some differences in argument.
Yes.
Oh, but after you speak, the proof in mathematics is a formal deduction.
Yeah.
Okay, but this is just an argument of knowledge which is probabilistic. So it's not going to be a solid proof.
Mm-hmm.
It's going to be something that with very high probability
Okay.
will be proved.
Okay.
That's the.
Okay. Actually, in zero proofs, the proofs has the feature of a probability. But here, the argument, why we use argument, there's another cryptographic reason that I will explain that probably tomorrow. And about here, we can use some basic intuition about why we use argument. So proof means that proof contain a lot of things, more than something, more than statement. For example, in a last format theorem, the proof can be very long and very long. We got many new mathematical tools inside. Even the author and the predecessor, they invented many different mathematical theory to eventually prove that theorem. So proof, basically we can extract many useful information from proof. But the argument does not. So yeah, the gentleman explained some basic ideas. The argument kind of more broader concept, and we just include some features from proof. We got argument. The point is that from argument we cannot extract something, but probabilistically we can know that the argument in fact proves something, but it contains less important things than proof. So here is the thing. For example, if we use theorem proof, for example, we use theorem proof. The prover uses some theorem proof, prove something encrypted data, for example, and then put it on chain, put the proof on chain, the argument on chain. So the question is, if in the future, for example, 100 years later, if the quantum computer is common, so can we decrypt the argument to get something meaningful, proved even 100 years before? The answer is no, because the proof is actually it's kind of argument. Even the quantum computer is common, will be common in the future, then we cannot get any meaningful information from it. So I think in the blockchain application, the argument is very, very important. So means that, the proof is actually contain minimal information to convince the verifier. So argument has some cryptographic definition. We will explain that later on. Probably tomorrow I will show you two different protocols. One is argument and the other one is proof. What about K? K is knowledge. Is knowledge. There's some term called proof of knowledge. So proof of knowledge is so let's go back to the statement that the prover wants to prove. So in the example here of the hash function, that actually this proof can be a proof of knowledge. Means that actually the prover proves he owns the witness, the private data. That the prover has knowledge instead of others. So prover does not only prove the truth of the statement, but also prove that the prover also has the knowledge. So the K means, okay, the proof of knowledge. So then we probably we may say another term called snark. Snark means the argument. So without K there, so snark means, okay, probably this proof does not ensure that the prover has knowledge. So in some application, this feature is very important. For example, the digital signature. So digital signature actually is the proof to prove that the prover has the private key. The prover, so if the prover only proves, okay, this signature is signed by someone, so that protocol cannot be used as a digital signature, right? So the prover has to prove that, okay, someone owns the private key, signed the message, plus the fact, okay, the prover himself has the private key instead of a private key from nowhere. Okay. Okay. Any questions so far? Okay, so I have 8 minutes. So any questions so far? Okay, we have 8 minutes, so we can show a modern Zig snark, the framework of modern Zig snarks. First of all, we have, for example, we want to prove the prover want to prove something like related to some commutation, right? General commutation, which is terminated circuit. But still, we have another option like ZKVM, quite popular today. And then, sorry. Yeah. And then we will have some algorithm or a theory to convert or to transform the constraints from a circuit and ZKVM to mathematical objects. So we give it a name, arithmatization. So the constraints, we will extract constraints from circuit or ZKVM and turn them into, by some arithmatization approaches, to turn them into mathematical objects like, for example, vectors, matrices, or the relationship between vectors and matrices. For example, the multiplication, inner product, and many other operations. And then usually we encode the matrices or vectors or other mathematical objects by using polynomials. But here I have to say, polynomial is not a math. Maybe if we don't care the efficiency, we can use some other approaches, not polynomial. But here is a picture of modern snarks, and polynomials are a very common and powerful tool for us to use. So here we got this layer called P, polynomial IOP. Polynomial IOP. IOP means IP, interactive protocol with O in between. O means oracles. We have oracles, like Oracle has something like an angel or something here. At this level, the protocol will, with the help with some trusted third party can assist to prove something. Yeah, okay. Okay, the angel as the oracle. With the oracle, the protocol can be much easier to design. Yeah, polynomial IOP. But in reality, there's no angel or oracle, right? No, we have to use a cryptographic tool to simulate an oracle. So we got this concept, polynomial commitment, commitment scheme to simulate an oracle. This was a huge breakthrough to separate the polynomial IOP from the polynomial commitments. A couple years ago, in polynomial IOP, pretty much like a Lego game. We have different protocols. We can compose them together to design or generate a more powerful protocol. But here, the polynomial commitments focus on using the cryptographic assumptions or mathematical tools to implement some very basic proof. For example, here we have the Frey KZG10, maybe quite popular in blockchain, and also lattice-based polynomial commitments and others. There's many. So below polynomial commitments, we got the algebra and math. Algebra. Yes. Sorry? Okay. Okay. Generally, the concept of ZK scenario, ZKP, is like maybe all of the layers called ZK scenarios, or only part of them. Or if we compare different ZK scenarios, different system that either require that we should compare them layer by layer. So the story of comparing ZK star or versus ZK snark, actually the comparison between Frey and the KZG10 at this level and polynomial commitment scheme level instead of ZK snark or ZK star. So if we're looking inside, and a different ZK snark system maybe share the same component or share the same layer. So we have to open the box, open the black box to see what is going on inside, or where are they're different. Maybe some ZK snark system they have multiple polynomial commitments candidates. if it's according to your application, you can choose different. For example, if you care about quantum computing efficiency, maybe you can choose Fry, but you don't care the proof size. But you care proof size very much, you should choose the KG10 and some other. Yeah. If you don't want this, the transit ceremony, so don't choose the KG10, choose bulletproof IPA or Fry or lattice space primitives. So I think, yeah. So far, any questions? So I think, yeah, sorry. Yeah, we may have 5 minutes for questions.
What's the role of the IOP wearable? I don't understand that. FRI is like Fourier transformation.
Yes. I mean, okay. Fry has IOP inside. Yeah, for sure. So Fry is kind of IOP, but here but Fry is inside polynomial cumulants. Actually, there are many modern constructions. Maybe we put another snark inside polynomial cumulants. So there are some approaches as protocols. They do this. So this is just a big picture. And Fry is definitely an IOP. This is called IOPP, right? It's one family of IOP of proximity. Sorry?
What's the role of the variable in the polynomial IOP?
Okay. With the role of oracle, okay. Inside polynomial IOP, the prover and the verifier, the prover wants to prove the properties of polynomials, right? On this layer, the prover and verifier, it's also an indirect proof. The proof has to prove the properties of polynomials. But actually, sometimes the prover wants to prove that the evaluation of proof. For example, the prover wants to prove that some polynomial f evaluate at some point like A. So if we are at the list level, the prover doesn't have to prove FA to the verifier. So instead, the verifier will ask an oracle. The oracle has F. Then the oracle answer FA to verifier instead of prover to prove. The only task of prover is send F to the oracle. And then all the following evaluation proofs done by the oracle. So it will simplify the protocol design, right? The proof only prove something, in a higher level by using evaluation proof. But the prover doesn't have to prove that because there is something called oracle. You can do this, and it can be checked multiple times by verifier. Yeah, that's the oracle. We call it polynomial IOP. Means that the oracle is all about the polynomial oracle. So no random oracle here, even. But maybe we can introduce random oracle. But here we just emphasize, okay, the oracle means polynomial oracles. Yeah. Okay, thank you. Any other question? No? Okay. Good. Okay. I think tomorrow, the next session, I will show you a minimal protocol called the Schnorr identification protocol to show a very basic. We will come back to this basic concept to understand something you said. Okay. Okay. Thank you for listening. Okay.